You click send on a message, you load a web page, it all feels instant, right? So seamless. But have you ever really stopped to think about what's happening under the hood in that split second? How does your data navigate the wild, chaotic digital world to arrive perfectly intact?
Well, it all starts with a journey through a hidden, layered world. Every single piece of data you send gets wrapped up and passed down through a series of layers, and each one has a very specific job to do. Today, we're zooming in on one of the most critical and honestly most overlooked of them all, the data link layer. This is the unsung hero that's responsible for the very first hop of your data's long journey.
So here's what we're going to cover. We'll see how this layer acts like the internet's local postman. We'll look at how it packages our data up, and then we're going to dig into two huge problems it solves that would make the internet basically unusable: traffic jams and data corruption. By the end, you'll see why it really is the network's unsung hero.
Okay, so to really get the data link layer, just think of it like your local mail carrier. It isn't worried about sending a package across the country or even across town. Its only job is handling that very first local leg of the journey, getting mail from your house to the next, or in network terms from your router to your internet provider's switch. It's all about communication between two directly connected devices. So here's the more formal definition, but the key things to remember are right there: local delivery and data frames. This layer is all about that first hop, making sure data gets safely between two devices that have a physical link, whether that's the Wi-Fi signal between your laptop and your router or an actual cable plugging two servers together. So if this layer is our local postman, how does it get a letter ready for delivery? I mean, you can't just send raw data into the wild. It has to be packaged up just right.
And this diagram shows it perfectly. Think of it like a set of those Russian nesting dolls. Your message, like "hi," gets passed down. The transport layer wraps it in something called a segment. Then the network layer puts that inside a packet. And finally, our hero, the data link layer, takes that whole packet and puts it in the final box for its local trip, the frame.
And, of course, every box needs an address. The packet inside has the IP address. That's the full global mailing address for the final destination. But the frame itself, for its short local journey, uses a MAC address. The easiest way to think about it is this: the MAC address is the specific house number on your street, while the IP address is the full mailing address with the city and country. The local postman only needs the house number. That's what the frame and its MAC address do.
But this whole local delivery system has two massive challenges that it absolutely has to solve. The first one is what we call flow control. Put simply, it's all about managing speed to prevent digital traffic jams.
Just think about it for a second. What happens if you have a brand new, blazing fast server trying to send a huge file to an older, slower computer? It's like one machine is firing off data with a fire hose, and the other one is trying to catch it all with a tiny cup.
Well, this is what happens: total overload. The receiver simply can't keep up. Its memory buffer fills to the brim, and it has no choice but to just start dropping data. Communication fails. The data link layer needs to be a traffic cop.
Now, the most basic solution is called the stop and wait protocol. It's very polite, but it's not very efficient. The sender sends just one frame, then it stops. It just sits there and waits, doing absolutely nothing, until the receiver sends back a little message called an ACK, which is just short for "I got it." Only then will it send the next frame. And this diagram shows us exactly why that's a problem. Look at all that red idle time at the bottom. That is just wasted potential. The entire connection is just sitting there doing nothing. I mean, it works, but it is painfully slow. So obviously, we need a better way, a method that can keep that communication link busy and keep the data flowing. And that is where the sliding window protocol comes in. It's a total game changer.
And the difference is like night and day. Instead of that polite one-at-a-time approach, the sliding window protocol lets the sender fire off a whole batch of frames, a window of them, without waiting for a single thank you back.
Let's see how this actually works. As you can see, Source System A has a buffer of frames ready to go. It doesn't just send frame 0 and wait. It sends a whole group, frames 0, 1, and 2, one right after the other, filling that pipeline with data.
Now watch what happens next. As the receiver gets and processes those frames, it sends back a single, efficient acknowledgement. It basically says, "Hey, I've received everything up to frame 2 and I'm ready for frame 3. As soon as the sender gets this, it knows the first batch made it safely, and its window slides forward, allowing it to send the next set of frames.
And this builds into this beautiful, continuous flow. The sender is always transmitting new frames as the oldest ones get the OK. And the result? A constantly moving stream of data that keeps the connection busy and efficient. That idle time problem? It's completely gone.
Okay, we've solved the speed problem. But what about that second huge challenge? The physical world is a messy, noisy place. What happens when our perfectly packaged frame gets corrupted during its journey?
You know, things like electrical interference or a weak signal can cause a bit to flip from a 1 to a 0 or the other way around. This is data corruption. A single flipped bit can make an entire frame of data totally useless, just like this disintegrating balloon. The receiver has to be able to spot this.
And the solution is some clever math. Using methods like a checksum or an even more robust one called a cyclic redundancy check or CRC, the sender performs a calculation on the data. It then attaches that result to the frame, kind of like putting a unique wax seal on an envelope. When the frame arrives, the receiver does the exact same calculation. If its result doesn't match the sender's seal, it knows the data was messed with in transit.
Knowing an error happened is one thing, fixing it is another. And this is where a system called Automatic Repeat Request, or ARQ, comes into play. The rules are pretty simple. If the receiver gets a corrupted frame, it sends back a negative acknowledgement, or a NAK. If a frame just gets lost entirely and the sender's timer runs out, it knows something went wrong. In either case, the solution is easy. The sender just sends that frame again.
So we've covered flow control and error control, sliding windows and checksums. I know it might seem a bit technical, but all of this connects directly to your experience online, every single day.
This quote from our source material really gets to the heart of it. The data link layer is foundational. It provides the reliable, error-free building blocks that all other, more complex network communication is built on top of.
And that brings us right back to the beginning. Every time you download a file and it isn't corrupted, every time you stream a movie that doesn't glitch out, and every time your message arrives perfectly, you have this invisible layer to thank. It's the silent, hard-working hero managing traffic and checking for errors on that first absolutely critical leg of the internet's journey.
So the next time you click send, maybe you'll think about that hidden world, that silent, super high-speed negotiation of frames and acknowledgements, all happening in milliseconds. The unsung hero that's just making sure your message safely makes its first, and most important, hop.